I want to start off today with a little conundrum, a little brain teaser, if you will. This is something you can think about in the back of your mind, or just pause your little video and try and figure out the answer to this. It's actually relevant to what we're going to talk about today. I learned this a few weeks ago when I went hiking with my kids. We went to the top of the highest mountain peak in Connecticut, which is actually not very high, but by elevation, we went to the highest mountain peak in Connecticut. But I read later on, the highest mountain peak in Connecticut is not the highest point in Connecticut. Think about that. All right? How could that be? This is the brain conundrum that I want you to think about. The highest mountain peak in Connecticut is not actually the highest point in Connecticut by elevation. And this is not some kind of a trick, all right? I'm not talking about there's some kind of a tower that somebody built or whatever. The answer is completely ordinary, all right? This is not a quirk about how elevation is measured or something like that, all right? No tricks about this, okay? It just so happens the highest mountain peak in Connecticut is not the highest point in Connecticut. How could that be? Think about it. Today we're going to talk about absolute extrema. This is actually the last topic that we're going to talk about concerning the derivative. It's been a long road. We talked a lot about relative extrema. Remember, those are, if you have a graph that looks like this, the relative extrema would be all of the points like this. These three would be relative minima. These two would be relative maxima. Those are the points which are bigger than or smaller than all the nearby points in terms of their y values. All right. Absolute extrema, though, that means not just the biggest, say, among the nearby points, but the biggest y value of the entire function, or the smallest, right? So not just the smallest of the nearby points, but the smallest overall. So actually, in this graph right here, this one right here, this is the absolute minimum. Absolute minimum. And this picture has no absolute maximum because these at the two ends they go up forever to infinity. So there's no absolute maximum. All right. So this in this bit we're going to talk about how do you find absolute minimum and absolute maximum points. The first thing you'll see is typical functions do not always have absolute minimum and absolute maximum when you look at the entire function, but they do if you are going to restrict your attention to just an interval. So let's talk a little bit about that. Here's a little something called the extreme value theorem. This, from a theoretical point of view, this is actually one of the classical theorems of calculus. It says if you have a function f of x and it's continuous, and if you consider only a closed interval in the domain, then f has an absolute minimum and maximum on that domain. Like just on that closed interval, there is automatically a largest possible value and a smallest possible value. Okay? Actually, the word closed is important if you consider open intervals. Typically, an open interval will exclude the endpoints, and in that case, you can miss out on the maximum value if it was going to occur on the endpoints. Let me just draw a picture here. I think we can fit it in right there, actually. Let's take, say, f of x equal x squared, right? This is a continuous function. But it does have an absolute minimum right there at the origin. It does not have an absolute maximum, though, because these two sides go up forever. And so there is no largest value of the y values of this function. But if we consider only a closed interval, which is what the extreme value theorem says, then automatically it will have a minimum and a maximum. Let's say this is my closed interval that I'm considering. And I'm only looking at the picture, just this much of it, from here and then to here. All right? If we consider only a closed interval in the domain, then on that domain, on this interval, there is a maximum and a minimum y value. So here the absolute minimum occurs at x equals 0, y equals 0, right here. And the absolute maximum occurs up there. The absolute maximum is at x equal 2, y equals 4. All right, the y value is 4 because that will be 2 squared. Okay, so if you have a continuous function and a closed interval, there is always an absolute minimum and an absolute maximum. So how do you find the absolute minimum and the absolute maximum? That's what we're going to do. All right, how do you find where the absolute minimum and absolute maximum are? Obviously, if you know what the graph looks like, then it's easy. You just look at the graph and you find the biggest y value and the smallest y value, and that's all there is to it. That's what I did here. What if you don't know what the graph looks like? This is a more interesting scenario. If you don't know what the graph looks like, here's something to notice, all right? This point right here was a relative minimum also, right? Because it is the smallest of all the nearby points. It also happens to be the absolute minimum. Okay, if you think about it, actually, what else could the absolute minimum be? The absolute minimum, if it's the smallest point overall, it should also be the smallest point of all the nearby points, right? So an absolute minimum should also be a relative minimum, and similarly an absolute maximum should also be a relative maximum. This one, though, isn't actually. It's an absolute maximum of the function, but it is not a relative maximum of the function. It just happens to be the absolute maximum because it's on the end of the interval. Okay, so because of this, it's actually easy to say where the absolute extrema appear. Okay, because of what I just said over here, here's a basic fact. The absolute extrema of a function always appear either at the relative extrema points, that would be like this one, or at the interval endpoints, that would be like this one. All right, so if your job is to figure out where the absolute extrema are, there's only a few possible locations where they could be, right? They could either be at the relative extrema. Where do these occur? They occur at the critical numbers, right? And we already know how to find those. Or they occur at the interval endpoints, and these are easy to find because you're always just told what the interval is, all right? So all you have to do if you want to find the absolute extrema, you find all the critical numbers, you also find the interval endpoints, which will be told to you, and you just decide which one is the biggest y value and which one is the smallest y value, and that's all there is to it. Find the absolute extrema for this function, 3x squared minus 12x plus 1, on this closed interval, minus 1 to 3. These absolute extrema problems will always be given to you in this way. A function and a closed interval, you find the absolute extrema. Okay, we're going to do what I just said. Find all the critical numbers and the endpoints, which are minus 1 and 3, and then just compare all the y values. What are the critical numbers? You're going to take the derivative, 6x minus 12, right? I want to know, when does the derivative not exist? The answer is never. It always exists because there's no denominators. When does the derivative equal 0? Let's do that. 6x minus 12 equals 0. Solve for x. You got 6x equal 12, x equal 2. All right, so this is the only critical number. And now what I'm going to do, I need to compare the y values at this point and at these 2 points. I'm going to just make a little chart here of x values, y values. So the chart should include all critical numbers, which in this case is just that one, and all interval endpoints. And compare the values. Compare the y values. So I'm going to need to plug each of these functions, each of these points into the original function to find their y values. You can do this on a calculator, or you can do it by hand. I mean, this one is not too hard to do by hand. Let's just do it. Well, pro tip, don't plug it into the derivative, all right? You will get wrong answers. You got to plug it into the original function. So I'm going to do f of 2. That will be 3 times 2 squared minus 12 times 2 plus 1. This will be 3 times 4, which is 12, minus, that's 24, plus 1. 12 minus 24 is negative 12, plus 1, negative 11, all right? Let's do the next one, f of negative 1. This is 3 times minus 1 squared minus 12 times minus 1 plus 1. Sorry, I'm encroaching here. I got minus 1 squared is 1, so this is 3. And then minus 12 times negative 1 is plus 12 plus 1. That's 15. 16 is the answer for that point. And finally, f of 3. I got 3 times 3 squared minus 12 times 3 plus 11. That would be 27 minus 24. No. 12 times 3 is 36. Okay, 27 minus 36 is negative 9, plus 1 is negative 8. So like that. Those look right to me. What are the, what's the biggest and what's the smallest? That's all you got to do. This right here, this is the biggest. This right here, this is the smallest. So this is going to be the maximum. This is going to be the minimum. All right. If you want a little sort of conclusion, you can say x equal minus 1, y equals 16 is the absolute maximum. And x equal 2, y equal minus 11 is the absolute minimum. That's it. Let's try another one. All right, let's do this one. It's very similar. There's actually one little thing that's going to come up this time that didn't come up last time, and that is when I make my chart at the end here, you should only consider the x values which are inside of this interval, all right? You don't want to give your answer, what's the absolute maximum? You don't want your answer to be something like x equals 3 is where the biggest value occurs, because we are only considering this function between minus 1 and 1, all right? Little something to keep in mind. That only comes up at the very end, but let's do the same process anyway. Find the critical numbers first. That will consist of taking the derivative and setting it equal to 0. The derivative is going to be here, 12x cubed plus 24x squared minus 36x, right? We want to set this equal to 0. Let's simplify this as much as we can. Factor everything you can pull a 12 out and also a x out. So 12x, what remains will be x squared plus 2x minus 3, right? And now this can factor, so 12x, and here we have x plus 3 and x minus 1. All right, we're going to set that equal to 0 and solve for x. I can do that. Okay, 3, 0, right? Come on there. That's an x. Okay, and that means you can get rid of the 12 if you want, because it's a 0 on that side. That means x equals 0, x plus 3 equals 0, x equal 1. I mean, x minus 1 equals 0, which amounts to x equal 1. So x equals 0 is a critical number, also x equal minus 3, and also x equal 1. Okay, what goes on the chart? Every critical number and also every interval endpoint. So minus 1 and 1 should go in there because they are the endpoints. And then also these three numbers, 0, minus 3, and 1. I guess you don't have to put 1 twice, right? It happens that the endpoint is also a critical number, whatever. Now, here's what I was saying at the very beginning. You should only consider the x values which are actually inside of this interval. So you do not need to plug 3 in. If you did plug this in, you might get an answer here which you think turns out to be bigger or smaller than everything else. And you might actually choose that one as the maximum or the minimum, but you shouldn't because we are only considering x values from minus 1 to 1. So I'm not trying to talk about that. Now you plug these guys into the original function and see what you get. When you plug in minus 1, this is going to be 3 minus 8 minus 18, which is something. That would be negative 5 minus 18, negative 23, right? When you plug in 1, you just get 3 plus 8 minus 18. That would be 11 minus 18, which is negative 7. And when you plug in 0, you get 0 throughout, all right? And as before, you choose the biggest and the smallest. This is the smallest, this is the biggest. So x equal minus 1, y equal minus 23 is the absolute minimum, and x equals 0, y equals 0 is the absolute maximum. That's that. One more of these. I just want to do one that was a slightly weirder kind of a function. Okay, you're going to do exactly the same process though. You don't have to worry about, oh, what am I going to do about that ln? Just do it. Don't worry about it. All right. We begin by finding the critical numbers. First, we take the derivative, f prime of x. You're going to have to do the quotient rule here, unfortunately, because that be a quotient. So do the quotient rule. Here's what it looks like. Now let's just simplify that a little, and you can cancel out an x here. This is our derivative, 1 minus 2 times natural log x divided by x cubed. We want to know when does this equal 0 and when does this not exist. Because of the denominator, x cubed in the denominator, we can say f prime does not exist when x equals 0, because that makes it 0 in the denominator. What else? When does the derivative equal 0? Also, actually, f prime does not exist when x is negative, because there's no such thing as log of a negative number. It doesn't really matter, though, because I'm only considering from 1 to 4, so x is never going to be negative. In fact, this doesn't even matter. X is never going to equal 0. So anyway, what about when the derivative equals 0? Let's do that. Here I have the derivative 1 minus 2 ln x over x cubed. Setting it equal to 0, solve for x. First thing, multiply x cubed over here, and it goes away. 1 minus 2 ln x equals 0. Let's add this over to that side. 1 equals 2 natural log x. I want to solve for x. Let's divide the 2 just to get this by itself as much as possible. Natural log x equals 1/2. And how do you solve this for x? You just have to rewrite this in this sort of exponential version. What does it mean when you say ln of x equal 1/2? That means x equals e to the 1/2. That's what this means. Remember what the natural log means. So that's your value of x. I solved for x. If you want, you can plug this into your calculator. You get something. What is it? I don't even know. I didn't do this on my calculator, but that's the value for x. Let's make the old chart, and then we should be finished. All right, my chart includes x values for the two endpoints, 1 and 4. It also includes all the critical numbers, the x values for the critical numbers. That was e to the 1/2. That's when the derivative equals 0. And 0 when the derivative does not exist. But like I said before, we're not going to consider this one because it's not between 1 and 4. I suppose you should check that e to the 1/2 actually is between 1 and 4. You can plug that into your calculator. It really is. Let's evaluate, find the y values for each of these. Some of these you can do by hand. I think one of them you have to do on your calculator. But for 1, you can do f of 1 equals natural log 1 over 1 squared. That's a 1. What is natural log of 1? Natural log of 1 is 0. So actually this whole thing is 0. So that y value is 0. Let's do f of 4. This one you cannot do by hand because of this numerator. Natural log of 4 divided by 4 squared, which is 16. That I put in my calculator, and I get something close to 0.08. Okay, so 0.08. And what about e to the 1/2? This one you can do by hand. F of e to the 1/2. You get ln of e to the 1/2 over e to the 1/2 squared. What is ln of e to the 1/2? This is just how the logs and the e's interact. You just get 1/2 on the top. And on the bottom, e to the 1/2 to the squared. Multiply the exponents, you get e to the 1. So this is, you could write it this way, 1 over 2e. All right, but actually you got to put this in your calculator anyway because you need to compare it with these other values. Put this in your calculator. This is approximately 0.18. So where's the minimum and maximum? This is the maximum. This is the minimum. So this is the maximum. This is the minimum. That's all there is to it. Did you think about that conundrum? Remember that conundrum? The highest point in Connecticut is not the highest mountain peak in Connecticut. It's a true fact. You know, the highest, let's just think about this in terms of extrema. All right, the highest mountain peak in Connecticut looks, you know, like that. All right, this point up here is actually, in terms of elevation, if you think of this as a function, it's actually a relative maximum, right? That's what the highest mountain peak in the state of Connecticut is. It's a relative maximum. But I said it's not actually the highest point in the state of Connecticut. That means that the relative maximum there is not the absolute maximum. All right, somewhere else there is an absolute maximum. How could it be that the absolute maximum is not the biggest relative maximum? Well, we've already seen actually how that could be is when it appears at the end point of the domain. That is to say, and this is a true fact, the state of Connecticut looks something like this, where the state line is maybe here, right? So the end of the state of Connecticut, here's New York, all right? The true fact of the matter is this is the highest peak in the state of Connecticut, but there are higher peaks in the state of New York, and you start going up the slopes of them while you're still in Connecticut. The highest point overall in Connecticut is here on the border between Connecticut and New York, all right? Higher than this peak, even though this point itself is not a mountain peak because it's not. It just happens to be on the border, and the absolute extreme points, the absolute maximum point either will occur on the peaks or on the border, and this one happens to be on the border. It's a great state we live in, isn't it?